Every rocket you watch starts its journey the exact same way. First, it rises straight up. It passes through the clouds, leaves the atmosphere behind, and heads toward the darkness of space. For us, there's no direction more natural than that. But the moment you get out into space, everything changes completely. Because in space, there's no absolute direction called up. Once you move away from Earth, up, down, left, and right only makes sense relative to where you're standing. The solar system doesn't have a ceiling, and it doesn't have a floor underneath it either. But here's a fact worth paying attention to. Almost every spacecraft humanity has ever sent continues to travel along that same thin, nearly flat plane, right alongside the planets. It's almost like some invisible force is holding them in that region. But there's no invisible wall out there. The real reason behind this is way more interesting. The planets move around the sun at lateral speeds of hundreds of thousands of kilometers per hour. That's why steering outside this plane is one of the most costly and complicated maneuvers you can attempt in a space mission. Going up isn't impossible, but the cost of doing it is incredibly high. So why does the whole idea of up disappear in space? And why have almost all the spacecraft we've launched so far stayed locked into that same plane of the solar system? But first, if you enjoy watching videos like this every night, go ahead and subscribe to the channel and drop a like, because your support makes a way bigger difference than you'd think. Because I'm here every single night to tell you even more. Let's begin. Right now, every rocket clip you've ever watched has been lying to you, and all it takes to catch that lie is a few minutes of your time. The column of flame rises, the body shakes, everyone on screen is looking the same direction. Up. Isn't that what you've been taught since childhood? A rocket takes off, punches through the sky and reaches space. Simple, clean, a straight line. But what I'm about to show you is going to tear that image apart. Because that straight climb you're watching quietly, invisibly, changes direction just half a minute after liftoff. And that change isn't an accident. It's the hidden key to all of space travel. Without this key, we couldn't get into space at all. When a rocket launches, it really does go up vertically for the first 30 seconds. But then, at a moment the cameras usually don't catch, the body slowly starts tilting sideways. That tilt is so gradual it's almost impossible to notice with the naked eye. But by the time the first stage separates, the rocket isn't pointing at the sky anymore. It's leaning toward the horizon. And once the engine's cut off and the vehicle reaches orbit, it's moving almost entirely sideways, parallel to the Earth's surface, at around 28,000 kilometers per hour. Stop and think about that for a second. Why does a rocket climb so hard just to end up turning sideways? The answer lies in the most misunderstood fact about space travel. Reaching orbit isn't about going high, it's about going fast. Altitude just gets you out of the thick atmosphere, it cuts down on drag. But what keeps you in orbit isn't altitude, it's that dizzying sideways speed. Almost all the energy a rocket burns goes into building horizontal speed, not vertical. Picture this. Imagine you could instantly teleport an object 400 kilometers above the Earth, but without giving it any sideways speed at all. You've always assumed that's basically how rockets fly, right? But that object wouldn't just hang there. It would start falling immediately, without a second's pause, and slam into the ground within minutes. Altitude means nothing without speed. What keeps the International Space Station up in the sky isn't its height, it's that incredible sideways sprint it's running non-stop, every single second. And this is where the first spark of cosmic dread shows up. Orbit is really just an endless fall. Astronauts aren't up high, they're constantly falling. But they're moving sideways so fast that the Earth curves away beneath their feet every second, and they never actually hit the ground. They fall and fall and fall and never land. Once that image sinks in, that simple idea of going up starts to crack. Because out there's no such thing as up, there's just an endless curve of falling. There's also an engineering side to this maneuver, and it's not poetic at all, it's pretty brutal. Engineers call it a gravity turn. The path a rocket follows is calculated in advance to convert that vertical climb into horizontal speed as fast as possible. After the first minute of flight, almost all the fuel being burned isn't going toward altitude anymore, it's going towards speed. This second act, the one broadcast feeds rarely show, is actually the real heart of the mission. While the cameras are showing you flames, the real story is happening off-screen, written along an angle you can't see. Think back to every rocket launch you've ever watched. Doesn't it always follow this exact script? Let's make this concrete. Picture a rocket. In its first minute, it climbs at almost a right angle. By the second minute, its body is already noticeably leaning, and by the 8th minute, its motion is almost entirely horizontal. It reaches the position and orientation it needs in just minutes. Compare that to a passenger jet and the difference is striking. A plane lifts its nose up as it climbs and mostly holds that angle. A rocket does the opposite. It stands up straight at first, then gradually lays itself down. That backwards logic goes so against human intuition that it still catches students off guard even in their first aerospace engineering classes. So why was this method chosen? Because the alternative costs way more. If a rocket stayed vertical the whole way up, it would fight needless drag through the thickest layers of the atmosphere, and then still have to make a massive direction change just to get into orbit. A gravity turn is a way of bending nature's own rules in engineering's favour, an elegant trick that turns even gravity's pull into orbital speed. Nature here is both enemy and ally. The same force pulling you down becomes, at the right angle, the very force that keeps you in orbit. Now let that sink in a little more, because there's an even more unsettling fact coming up. This need for sideways speed isn't just about the moment of launch. The Earth itself is drifting sideways around the Sun at 30 kilometers per second. Right now, as you're watching this, you're drifting through space right along with it. So every rocket, every satellite, every human-made object inherits that massive sideways speed before it's even launched. You're not stepping out into some empty, directionless void. You're jumping into a river that's already flowing at incredible speed. And changing that river's direction, as we'll see later, costs way more than you could imagine. So why does this matter so much? Because in the footage you're about to see, even in the latest launch recordings shared by real space agencies, you'll spot the same illusion. In SpaceX's Starship launches, in the European Space Agency's Ariane 6, even in India's latest lunar missions, the cameras always show the vertical climb, because the human eye and the human camera both love vertical. But the real story always drifts to the edge of the frame, leaning toward an angle you can't see. This is also a good point to bring up a historical contrast. For centuries, humanity imagined the sky as a fixed, unchanging ceiling. Ancient astronomers thought the stars were nailed to some giant dome, and getting past that dome was almost a religious impossibility. Today, though, we know there's no fixed point in the sky at all. Everything, at every moment, is orbiting something else. The gap between that old reassuring fear of a motionless dome and today's dizzying reality of a universe that never stops spinning completely changes how humans see their place in it all. Our ancestors looked up at the sky and felt safe. We look up at that same sky and see, not stability, but an endless fall. The human side of this is just as unsettling as the physics, because this rule isn't just about rockets. Right now, as you're reading these words, you're drifting around the sun at 30 kilometers per second too, and you don't feel a thing. The ground under your feet gives you this endless sense of security, but the planet holding that ground, the one holding you, is falling through space without stopping. The contradiction between that solid ground you feel safe on and that dizzying speed hiding underneath it might just be the most unsettling thought this episode leaves you with. Now let's zoom out even further, because this is where the real dizziness starts. If you squeeze the entire history of Earth into a single day, the invention of rockets would land in the very last second of the night, while the Earth's silent, unstoppable sprint around the sun would run non-stop from the start of that day to the end. Humanity spent almost its whole history not even realizing this sprint was happening. Now think about this too. Changing that sprint, breaking out of the plane the planet follows, carries a cost that's almost impossible, as you'll see in later episodes. Do you think humanity will ever be willing to pay that price? Or are we never getting out of this lane? I'd really love to hear your guess in the comments. I want to stop here and ask something. If the direction you call up actually loses its meaning within seconds, is there really such a thing as up? Or is that just a shirt an earthborn brain has dressed the universe in? The answer to that question is going to confront you with something even deeper and even more unsettling in later episodes. But first, you need to get this idea clear in your head, because our next stop is the inside of orbit. There, in the middle of weightlessness, you'll see exactly how the human brain completely loses track of up and down, and how astronauts wrestle with a view of Earth that changes 16 times a day. Right now, 400 kilometers above the Earth, 6 people are floating around unable to tell up from down, and their brains are still trying to accept that loss. Picture an astronaut who's just arrived at the International Space Station. The moment they step out of the capsule, their body goes looking for the one truth it's known for years, where down is. But it can't find it. The balance organ in the inner ear, that quiet compass that's never once shut up your whole life, suddenly stops sending signals. Some astronauts wake up for days with a constant feeling that they're falling. Some think the room is upside down, that they're the ones stuck to the ceiling. This isn't just a matter of getting used to something, it's the brain losing the one reference point it's trusted since the day it was born. So why does this happen? Because gravity doesn't disappear up there, it just becomes something you can't feel. An object in orbit around the station is still carrying about 90% of the gravity it would feel on the ground. Astronauts aren't escaping gravity, they're falling along with it. The station, everything inside it, every drop of water, all of it is falling at the exact same speed. And that's why none of it presses down on anything else. If an elevator cable snapped and everyone inside went into total freefall, they'd feel that exact same weightlessness inside that elevator. The difference is, the elevator hits the ground a few seconds later. The station never hits anything, because the ground keeps curving away underneath it. And here's where humanity's solution is about as human as it gets. We just made up an agreement. Inside the station, floor and ceiling are marked out with certain colours. An orange surface counts as the floor, a white surface counts as the ceiling. Handles are placed according to this made-up direction, and text is oriented upright based on it. But this isn't a law of physics, it's just a convention the crew agreed on so they can understand each other. If an astronaut rotates 90 degrees, the surface they just called the ceiling instantly becomes their floor, and nothing in the universe objects to that. In a room with no gravity, up and down turn into a kind of etiquette, decided by however the two people happen to be positioned. And here's a striking human contrast. On Earth, you never have to agree with anyone about direction. Gravity makes the same call for everyone, and that call isn't up for debate. But in orbit, two people can look at the exact same control panel and describe completely opposite directions to each other, because each of them has their body angled differently. The gap between Earth's strict, no-argument system and orbit's fragile system that needs constant negotiation shows just how borrowed that sense of security really is. Now let's zoom out a bit more. Because the station itself isn't tracing some fixed line around the Earth, it's actually passing over a constantly changing geography, and that shatters the idea of direction all over again. The station's orbit is tilted 51.5 degrees relative to the equator. That tilt wasn't picked at random, it was carefully calculated so it could be reached from launch sites in both the US and Kazakhstan, and so it could pass over a wide stretch of the Earth. But that tilt has a consequence, and it's almost uncomfortably poetic. The station completes a full loop around the Earth every 90 minutes. In those 90 minutes, the crew sees the Mediterranean first, then the endless steppes of Central Asia, then the emptiness of the Pacific Ocean. If they look out the same window at the same time the next day, they get a completely different view, because the Earth keeps spinning underneath their fixed orbit without stopping. The orbit stays exactly the same in its own plane, while the Earth underneath it keeps sliding by, almost like the planet itself is trying to slip out from under the station's fixed gaze. Think of this as a historical contrast. In the past, sailors relied on the stars to find their way, because the sky was fixed, the North Star was always in the same spot, and that fixedness gave them a sense of security. Today, though, an astronaut's down can shift from a desert to an ocean within minutes. The gap between that unchanging sky the sailor trusted and that slippery sense of direction an astronaut has to redefine every 90 minutes shows just how fundamentally humanity's relationship with the universe has changed. Think about it this way. If an astronaut tried to define down based on some specific country or some specific desert, that definition would only hold up for a few minutes before becoming completely meaningless. Nothing about the station's own motion ever changes. What changes is which point on Earth that motion happens to line up with at any given moment. Direction isn't some fixed property of your surroundings. It's a fragile relationship between the observer's motion and the object they're circling. And that relationship never stops shifting, not even for a second. Let's think about this using a map. The station's ground track, the imaginary line it traces across the Earth's surface below, shifts a little to the west with every orbit, because the Earth keeps spinning on its axis while the station stays in its own fixed plane. This shift is so regular that engineers can calculate, days in advance, exactly which hour the station will pass over which country. But strangely enough, that precision doesn't ease the loss of direction. If anything, it makes it even more obvious. Because the only thing that's mathematically predictable is the fact that down will keep changing, not what down actually is. This is the second big crack in the whole idea of up. In the first episode, you saw that rockets don't actually go straight up the way they appear to. Speed was everything, and altitude barely mattered. Now we're seeing that even once you reach orbit, the direction you call down isn't some fixed fact. It's a variable you constantly have to recalculate. The center of the Earth is still there, sure, but your relationship to that center gets rewritten every single moment based on which point on Earth you happen to be over. Let's make this a bit more concrete. The station orbits the Earth 16 times a day. That means the crew sees 16 sunrises and 16 sunsets every 24 hours. Just think about it. Down here on Earth, a person experiences sunrise once a day, always at the same rhythm, and their body sets its clock around that rhythm. But up there, inside that thin metal shell, the sun rises and sets all over again every 90 minutes. The body clock getting interrupted that often shows that it's not just direction that falls apart up there. The sense of time falls apart right along with it. Astronauts constantly have to recalculate not just where they are, but when they are. Now let's touch on a scientific contrast. On Earth, the line between order and chaos is clear. Gravity represents order, and its absence points to chaos. But in orbit, that distinction flips. Up there, real order comes from an agreement the human body builds artificially. From the outside, from coloured markings, fixed handles, and a shared idea of what counts as the floor. Once natural order, that strict hierarchy gravity forces on you, disappears, humans are forced to invent their own order. Chaos, it turns out, doesn't come from a lack of something. It comes from having too many equally valid options. When every direction is just as valid as every other, no direction is special anymore. Let's push this idea a bit further. Even ground control teams have to stick to this same agreement when they're communicating with the crew. Saying, turn right or look up has an obvious meaning down on Earth, but in orbit you first have to clarify exactly which up you're talking about. That's why every procedure inside the station, every emergency instruction, is written according to this artificial floor-ceiling agreement. If that agreement were ever forgotten, or if two crew members were working with different orientations, even the simplest repair job could turn into dangerous confusion. Here's the most unsettling part. This disorientation isn't happening on some star millions of kilometers away. It's happening on a station you can watch on a live stream, right next door to Earth. Space isn't as far away as you think. This fragility starts just above the atmosphere. If that idea unsettled you too, if you just realized how fragile the directions you trust actually are, don't forget to like this video and subscribe to the channel, because content like this only keeps going thanks to your support. One more thing worth adding, this loss of direction isn't just a scientific curiosity, it's a psychological struggle too. According to current reports from space agencies, astronauts coming back from long-duration missions still have to deal with this messed-up sense of direction for a while, even after they're back. Returning to Earth means the body has to relearn its old habits all over again, which shows that once the human brain loses its sense of direction, getting it back isn't instant either. What's lost isn't just information, it's a sense of trust. So where does this feeling of loneliness come from? The answer is simple, and just as unnerving. Because in there, inside that metal capsule, the rest of the universe doesn't care about you. The stars won't tell you which direction is right. The sun won't point you anywhere. You have to invent your own floor, your own ceiling, because the universe isn't giving you a single clue. And maybe the biggest lesson hidden inside that loneliness is this. we learn to rebuild that sense of security not from some outside signal, but from within ourselves. So, are the distances between the planets really what they seem? Or is there something a lot more unsettling hiding behind those numbers? In the next episode, we're going to find out together that the real distance between planets is actually way more unnerving than you think. Don't forget to subscribe to the channel and like this video so you don't miss out on getting to see it first. But here's the truly shocking part. The station's fragility is actually the smallest, closest example of something much bigger in the universe. Because the farther you get from Earth, the idea of direction doesn't just get blurry, it dissolves completely, step by step. The Earth itself shrinks, the Sun's gravity starts taking over, and eventually even the object the word down is pointing at changes entirely. As you head toward the Moon, Earth still remains the biggest object in the sky, but that dominance keeps fading, and at a certain point, Earth's gravity loses out to the Sun's, and with no signal, no line, nothing marking the moment, the word down quietly shifts from Earth to the Sun. That transition is so smooth that no alarm goes off, no boundary ever shows up. One moment you belong to Earth, the next moment you belong to the Sun. In a bit, we're going to walk through this unravelling step by step, from Earth to the Moon, and from there, all the way out to the farthest corners of the solar system. Where do you think this disappearing act finally ends? Is there some point where we can stop and say, this, right here, is the real up? Or does this disappearing just keep going forever? I'd genuinely love to read your thoughts on this in the comments. Right now, a spacecraft just a few hundred kilometers above Earth is still acting like it belongs to your planet. Down is clear, gravity is still in charge, but that sense of belonging is a lot shorter lived than you'd think. Because the farther out you go, the word up quietly, invisibly starts dissolving, and there's nothing that can stop it. In low Earth orbit, around 400 kilometers up, the planet still fills half the sky. At this distance, gravity is almost as strong as it is on the surface. It's only about 10% weaker. An astronaut can easily work out which direction points toward the center of the Earth. Down still has a clear meaning here. But that clarity is kind of an illusion, because the moment you go higher, it starts changing. Go up to 36,000 kilometers, geostationary orbit altitude. This is the zone communication and weather satellites prefer, because up here a satellite moves in perfect sync with the Earth's rotation and just stays parked over the same spot in the sky. But behind that practical perk, something a lot deeper is shifting conceptually. Earth doesn't fill the window anymore. It looks more like a bright marble hanging in space. Gravity out here is only about 3% of what it is on the surface. The planet's still there, it's still defining a down, but it's not calling all the shots anymore. The sun looks brighter, the stars are still fixed, but Earth's visual dominance is quietly slipping away. Now picture a trip all the way to the Moon, about 400,000 kilometers out. Earth is still a clearly visible sphere in the sky. Remember that famous photo from the Apollo missions, half of Earth in shadow, half lit up, hanging there in the deep dark of space? That image hits people hard because there's still a familiar sense of down in it, but that dominance has already started fading. Keep going. Get out to about 1.5 million kilometers and you cross an invisible boundary. It's called Earth's sphere of gravitational influence. Past this point, a spacecraft is no longer orbiting Earth, it's orbiting the Sun. Down no longer points to the planet you launched from, it points to the star at the center of the solar system. This crossing is invisible. No line, no warning, no physical marker of any kind. One moment Earth is defining your direction, the next moment the Sun is, and it happens without you ever noticing. That's just how sneaky this concept of up really is. You don't even realize you've walked through a door, but the room you left behind doesn't recognize you anymore. So keep going. Let Earth shrink down into a little blue dot, then let it become indistinguishable from the stars in the background. Now down points toward every direction that's away from the Sun. But that's not one single direction. It's an infinite number of arrows radiating outward from a central star in every direction at once. There's no single up, there's only outward. And outward doesn't tell you which way to go, it only tells you which way you're moving away from. Think of water shooting out of a fountain in the middle of a plaza. Every drop heads outward, but none of them is heading in a more correct direction than any other. So, does the solar system itself have some shared vertical? This is where things get genuinely unsettling. Astronomers use 3 different reference planes, and none of them line up exactly with each other. The first is the ecliptic, Earth's orbital plane around the Sun. The second is the invariable plane, defined by the combined angular momentum of every object in the solar system. This plane is basically set by Jupiter. Because Jupiter has more mass than all the other planets combined, the ecliptic is tilted about 1.5 degrees away from this invariable plane. That sounds like a tiny difference, but it points to a conceptually devastating fact. Even Earth's own orbit isn't some universal reference, it's just a reference. The third plane is the Sun's own equator, and this is where things really get weird. The Sun's rotational axis is tilted about 7 degrees away from the planet's orbital plane, which means even that giant star at the center of the solar system, holding more than 99% of all its mass, doesn't share the same vertical as the planets spinning around it. If even the biggest, most dominant object in the whole system can't offer up a universal up, then the whole idea that such a thing even exists was a mistake from the start. Scientists still can't fully explain why this misalignment exists, but one of the leading theories is that a passing star, or early magnetic interactions, caused this small tilt back when the solar system was still forming. Now bring this back to your own planet. Earth's rotational axis is tilted 23.5 degrees relative to its orbital plane. This tilt is what creates the seasons, but it's also hiding an unsettling fact. If you stood at the North Pole and pointed straight up, you wouldn't be pointing perpendicular to the solar system, you'd be pointing at some odd diagonal angle. That's a direction that only makes sense because of Earth's own rotation. It has no universal meaning at all. And think about this. For centuries your maps have always put north at the top. The pole always drawn on top, the south always drawn on the bottom. But Earth is a sphere spinning in space, and no point on its surface is naturally higher than any other. This is purely a cultural habit, an arbitrary call geographers made centuries ago, and that habit is so deeply ingrained that people carry it over to the solar system without even questioning it, imagining that there's an up and a down out there too. In the same way, whenever you look at diagrams of the solar system, you always see it from a bird's eye view, with the planets drawn in neat circles. But that view from above is really just an arbitrary angle, a picture chosen from a reference point called ecliptic north. If you drew that same system from the side, the planets would look like a thin strip, almost stacked right on top of each other, and that image would be just as accurate as the other one. So, would you still trust that classic world map with north on top, or would you now admit it's really just a convention? Share your thoughts in the comments, because this question opens up a much deeper discussion than it seems to. Here's the truth. The ecliptic, the invariable plane, and the Sun's equator are 3 separate surfaces, each only a few degrees apart from the others. Up close they look aligned, but none of them is any more correct than the others. Picking one and calling it the true horizontal is a purely human decision, not a physical necessity. Just like a mapmaker chose to put the North Pole at the top of the map, astronomers chose to use the ecliptic as their reference. Another choice was just as possible. At this point, that clear, calculable idea of down you had in low orbit is already ancient history. It's been replaced by a constantly shifting, relative relationship that depends entirely on which object's gravity happens to be dominant. Between Earth and Mars, the Sun dominates. Once you get close to Jupiter, Jupiter takes over. Out in interstellar space, no object dominates at all, and the whole concept just becomes meaningless. Think about Voyager 1, out there cruising through interstellar space right now. Even the Sun is basically just another star to it now, bright, but with no authority, just a distant point of light. And this is exactly where we get to the real heart of the story. Because if even the solar system itself doesn't have a shared vertical, then the question of why all the planets ended up packed into that same flat plane becomes even more unsettling. Is that flatness just a coincidence? Or is it a trace of something far more deeply rooted, going all the way back 4.5 billion years? The answer to that question goes all the way back to the birth of the solar system, to how a chaotic cloud of gas turned into the shape we see today, and we're about to dig into those roots. Right now, as you're reading these very words, everything in the solar system, including you, is hurtling through space at 30 kilometers per second. You don't feel that speed because everything is moving at the same time, in the same direction. But this quiet, unnoticed speed is the legacy of a cosmic accident that happened 4.5 billion years ago. And the story of that accident explains why the word up is so fragile today. In the beginning, there were no planets. There was no sun. There was no Earth. There was just a massive, cold, almost completely empty cloud of gas and dust. Scientists call it the solar nebula. This cloud was so huge that it would have taken light years to cross from one end to the other. The material inside it was unbelievably sparse. Most of the cloud was hydrogen gas, with bits of carbon dust, silicate fragments, and ice crystals scattered around, leftovers from stars that had died long before. The temperature was close to absolute zero, meaning there was almost no heat at all. This cloud wasn't sitting still. Like every structure in the galaxy, it had a slight spin. It was so slow that you couldn't have noticed it even watching over an entire human lifetime. But gravity was patient, and over time it got to work. Somewhere, maybe the shockwave from a nearby star exploding, maybe just some random clump getting denser inside the cloud itself, something triggered the collapse. And that collapse didn't happen all at once. It played out over roughly 100,000 years, slow at first but steadily picking up speed. In the beginning, the motion was almost impossible to notice. The outer edges of the cloud started drifting inward slower than a walking pace. But as matter got closer to the center, density went up. And as density went up, gravity got stronger, and stronger gravity sped up the inward collapse even more. It was a self-feeding loop, a natural consequence of one of the most basic laws in physics. As the cloud collapsed, it started heating up. Gravitational potential energy was converting into heat. The temperature at the center climbed to tens, then hundreds, then thousands of degrees. This dense region glowing at the center wasn't a star yet, but it already had enough mass to gravitationally dominate everything around it. This is called the proto-sun. It would take another 30 to 50 million years for it to become an actual star, meaning for its core to hit that 10 million degree threshold needed to start converting hydrogen into helium. But the real magic was in what happened to all the leftover material while the protosun was forming. And this is where one of the universe's most fundamental and most unforgiving laws kicks in: the conservation of angular momentum. To understand this, picture a figure skater. Spinning with their arms stretched out, they rotate slowly. Pull the arms in, and with that same amount of energy, they start spinning way faster. As mass moves closer to the center, spin speed automatically goes up, no extra force required. And that's exactly how the collapsing nebula behaved. As gravity kept pulling the cloud inward, that barely noticeable initial spin kept getting more and more intense. The cloud just kept speeding up and up. But this collapse wasn't the same in every direction. Along the rotation axis, meaning north to south, the cloud could collapse freely because gravity was pulling matter straight toward the center, and the spin wasn't resisting that motion at all. But along the equatorial plane, it was a different story. Matter out there was spinning so fast that centrifugal effects were resisting the inward pull. It was spinning too fast, not slow enough to get pulled into the center. The outcome was inevitable. Matter along the axis collapsed quickly, while matter along the equatorial plane stayed spread out. Over the course of a few thousand years, that thick, roughly spherical cloud turned into a thin, rapidly spinning disk, with a dense clump of mass building up at the center that would eventually become the sun. The disk was hot near the center and cold toward the edges, dense near the center and sparse farther out. But most importantly, it was completely flat. This structure is called a protoplanetary disk, and astronomers don't just know about it in theory, they've directly observed it around other young stars. One of the most powerful telescopes we have today, the ALMA telescope array, actually photographed exactly this kind of disk around a young star roughly 450 light-years from Earth. In the image, you can see a thin, circular disk full of dark rings, swept clean by young planets still in the process of forming. That image is basically a near-identical snapshot of what our own solar system looked like 4.5 billion years ago. Everything that formed in that disk inherited this geometry. Dust grains collided, and in that near-empty environment, the collisions were gentle enough that instead of shattering, the grains stuck together. Millimeter-sized clumps grew into centimeter-sized pebbles, and those pebbles grew into meter-sized rocks. As these growing bodies started pulling in more material with their own gravity, the whole process sped up. Within a few million years, the disk was packed with thousands of kilometers worth of objects, the seeds of the future planets. And every single one of these objects ended up orbiting within the plane of the disk. There really wasn't any other option. They were all made from material that was already moving at the disk's own spin speed. Flatness wasn't imposed on them from the outside. It was baked into them from the very first moment they formed. They were children of the disk, and they carried the disk's geometry in their orbits like a kind of genetic inheritance. So can we still see that legacy when we look at the planets today? Yes, and the numbers are honestly striking. Venus's orbit is tilted only about 3 degrees relative to our reference plane. Earth is basically treated as that plane itself. Mars's tilt is under 2 degrees, Jupiter's is around 1.5 degrees, Saturn's is about 2.5 degrees, and Uranus and Neptune's don't go past a few degrees either. So almost the entire mass of the solar system, spread across a system tens of billions of kilometers wide, is packed into a narrow band just a few degrees thick. Here's the easiest way to picture it. If you think of the solar system as a vinyl record, that record is thousands of kilometers wide but only a few meters thick. The proportions really are that extreme. The one exception is Mercury, tilted about 7 degrees relative to the plane. You could call it the rebellious kid of the inner solar system. But even its little rebellion is pretty modest on a cosmic scale. Go even further out, and the dwarf planet Pluto sits at a 17-degree tilt, Eris at 44 degrees. These objects are the exceptions, and their strange tilts, as we'll see in a future episode, tell stories of gravitational encounters and troubled pasts. So why is it so surprising that this many objects, spread across this much space, all end up spinning in the same plane? Because logically, it didn't have to turn out that way. But the universe doesn't run on our logic. If the sun had just randomly grabbed objects from every direction, you'd expect a spherical spread of planets coming and going from every angle, a chaotic swarm, not a disk. But the system looks like a disk. And the reason for that comes straight from how the system was born. Everything took shape from a single spinning cloud, bound by the unforgiving logic of angular momentum. Right now, way out past Neptune's orbit, billions of kilometers from the sun, trillions of icy objects are quietly spinning in the dark. Some of them still carry the memory of that flat disk from 4.5 billion years ago. Others tell a completely different story, a violent, chaotic one, carrying the scars of a massive upheaval that happened while the planets were still young. This region beyond Neptune is called the Kuiper Belt, stretching from about 30 to 50 astronomical units from the Sun. At first glance, it still looks pretty flat. Most of the objects out here orbit together in a band close to that reference plane we use to define the planet's orbits. Sure, their tilts are a bit bigger compared to the planets, some 10 degrees, some 20, even up to 30 degrees in some cases. But the overall population still shows a clear clustering toward that plane. The Kuiper Belt basically still carries the memory of that old disk, shaped by the same processes, a direct continuation of the material that built the planets. But when we take a closer look at this belt, we find two very different characters living side by side. And comparing these two groups might be the most striking example of how the solar system's flatness erodes with distance. The first group is made up of what scientists call the classical Kuiper belt, or the cold population. These sit about 42 to 48 astronomical units from the Sun, with pretty low tilts, generally not exceeding 5 degrees, on nearly circular orbits. It looks like these objects formed right where they are, without any major planet ever disturbing them, and they've preserved the calm, orderly geometry of that original protoplanetary disk exactly as it was. They're basically fossils, preserved inside billions of years of ice. Their low tilts and calm orbits show that these objects were never seriously disturbed in the past. They're sitting in that plane because they've always been there, and nothing ever pushed them out of it. The second group paints a completely different picture. Scientists call it the scattered disk, and the name really fits. These objects have extremely stretched out, elliptical orbits, sometimes bringing them in close to Neptune's neighbourhood, sometimes flinging them hundreds of astronomical units from the Sun. Their tilts are also way bigger, 20, 30, sometimes even over 40 degrees. These objects weren't born on these orbits. They got thrown onto them during a massive upheaval early in the solar system's history, through close gravitational encounters with Neptune. This story goes back around 4 billion years, to a period when the outer solar system went through a major reshuffling. Back then, the giant planets were migrating in their orbits, and as Neptune moved outward, it ploughed through what was then a much denser belt of icy objects. As it passed through, it flung the countless objects it encountered off in every direction. Some got thrown inward and turned into short-period comets, or got swallowed up by the giant planets. Some got flung outward and either joined the scattered disk or got kicked out of the system entirely. And some ended up on orbits that took them way above or way below that original plane. You can think of the scattered disk as a kind of transition zone, somewhere between the classical Kuiper belt's orderly flatness and the truly random Oort cloud we're about to get into. Objects here still show a slight statistical lean toward lower tilts. There are somewhat more objects near the plane than far from it, but the spread is wide and messy. The disk still remembers that old plane, but imperfectly, like an old photo that's partly gone blurry. Neptune's gravity was strong enough to tilt orbits by dozens of degrees, but not strong enough at these distances to completely randomize them. This gradual shift, going from flat to a thick band to a spherical spread, is one of the most elegant features of the solar system, and it directly shows how the planet's gravitational influence weakens with distance. Close to the Sun, the planets are massive and there are a lot of them, so orbits stay flat. Gravitational interactions happen often, and they keep suppressing any unusual tilts. In the Kuiper belt, the last major planetary influence comes from Neptune, and it stirs up the population without fully randomizing it. Beyond the Kuiper belt, no planet's gravity can do much of anything. Instead, the galaxy's tidal forces and passing stars take over, gradually wiping out whatever's left of the disk's flatness. And that's exactly where the Oort cloud comes in. This massive shell of icy bodies they thought to stretch from around 2,000 to 100,000, astronomical units from the Sun, theoretical, but backed by solid evidence. And this cloud is the exact opposite of everything we've described so far. Not flat, spherical, long-period comets, those rare visitors that show up in the sky every once in a while and usually don't come back for hundreds or even thousands of years, are thought to come from the Oort cloud. And these comets reach the inner solar system from every direction, from above the plane, below it, from the side, at steep angles, at shallow angles. There's no preferred plane at all. The Oort cloud wraps around the Sun like a massive scattered shell, and the objects inside it orbit at every tilt imaginable. This spherical structure carries the marks of a pretty turbulent past. The objects in the Oort cloud weren't born there. They formed much closer in, inside that original protoplanetary disk, in regions near the giant planet's orbits. But during the solar system's first few 100 million years, gravitational encounters with Jupiter, Saturn, Uranus, and Neptune flung these icy bodies onto extremely stretched out orbits. Some got kicked out of the system entirely. Others got flung out to unbelievable distances but stayed weakly bound to the Sun's gravity on orbits that take millions of years to complete. Once these objects reached these extreme distances, their orbits weren't primarily being shaped by the Sun and planets anymore. At tens of thousands of astronomical units out, the tidal pull of the Milky Way galaxy itself starts to matter. The galactic disk's slow gravitational pull, combined with the occasional disturbance from a passing star, gradually rotates and randomizes these distant objects' orbital planes. Over billions of years, a population that got flung out of a flat disk turned into a spherical cloud with orbits pointing every which way. So even these outermost icy objects, over time, broke free from the solar system's orderly plane and found their own chaotic kind of freedom. Maybe even out at the farthest edges, no structure stays the same forever. So are the distances between the planets really what they seem? Or is there something a lot more unnerving hiding behind those numbers? In the next episode, we're going to find out together that the real distance between planets is actually way more unnerving than you think. Don't forget to subscribe to the channel and like this video so you don't miss out on getting to see it first. The inner parts of the Oort cloud, out to a few thousand astronomical units, still carry a bit of that original disk's memory, roughly close to the reference plane, but bent and warped by galactic tidal forces. But the outer Oort cloud, beyond 10,000 astronomical units, is completely isotropic, truly spherical, with no preferred plane at all. This shift from flat to spherical marks the boundary where the Sun's gravitational dominance ends and the galaxy's broader influence takes over. So what does this contrast tell us? The difference between the inner solar system's flat structure and the Oort cloud's spherical structure really clarifies what flatness actually means here. The solar system is flat because it was born from a disk, and the conservation of angular momentum forced that shape on it from the very start. The Oort cloud is spherical because outside forces had billions of years to erase that original flatness. The planet's flat plane isn't some universal law. It's a historical trace left behind by the conditions the system formed under. And that trace only survives in the inner solar system because nothing out there is strong enough to disturb it. The Sun's gravity dominates, and the galaxy's tidal forces are basically negligible. Which brings us to an interesting question. If the planets orbit in a plane, does that mean there's something stopping an object from moving above or below that plane? Is the ecliptic some kind of valley pulling objects back into it? The answer is no. There's no restoring mechanism keeping objects in the plane. If you put a satellite on a perfectly circular orbit at Earth's distance from the Sun, but tilted 90 degrees to the ecliptic, that orbit would stay stable for billions of years, with no tendency to flatten out at all. The Sun's gravity doesn't care about the ecliptic. It pulls equally in every direction. A 90-degree orbit is just as gravitationally valid as a 0-degree one. The reason objects stay in the plane isn't because the plane pulls them back. It's because they've simply never existed anywhere else. They formed in the disk, they inherited the disk's orbital motion, and nothing ever gave them enough energy to leave it. The ecliptic isn't a valley, it's a starting point. And leaving it requires energy that the solar system's natural processes rarely provide. Of course there are exceptions. Comets coming from the Oort cloud arrive at extreme tilts because they got gravitationally scattered over billions of years. Some asteroids got pushed onto unusual orbits through close encounters with the planets. The dwarf planet Eris's 44-degree tilt reflects gravitational interactions in its past that flung it far from the plane. But these exceptions actually prove the rule. Every object with a big tilt got that way through some specific gravitational event, a close encounter, a resonance, or a scattering process. None of them just drifted upward on their own. Right now, even as you're reading this line, your body is orbiting the sun at 30 kilometers per second. That's over 110,000 kilometers an hour. You don't feel it because you, your chair, the room, the entire planet are all moving at that same speed, in that same direction. But this invisible speed is at the very heart of why spacecraft almost never leave the planet's shared plane. This speed isn't optional. It's not something you get to choose. Every spacecraft that leaves Earth automatically inherits this speed the moment it departs, born straight into the same orbital current that's been carrying the planet around the sun for 4.5 billion years. There's no 0 point, no empty starting moment where every direction is equally available. This inherited speed is the single most important fact about getting around the solar system. It's what decides what's easy, what's hard, and what's damn near impossible. Moving along the ecliptic plane is relatively easy. If a spacecraft fires its engines in the same direction as Earth's orbital motion, it picks up speed and its orbit widens outward, letting it reach Mars, Jupiter, Saturn, and beyond. If it fires its engines against that motion, it loses speed and its orbit shrinks inward toward Venus or Mercury. These maneuvers work with the existing speed. They add to it or subtract from it, but they don't change its basic direction. The spacecraft stays on the ecliptic, following curved paths shaped by the sun's gravity, and reaches its destination with impressive efficiency. Pretty much every interplanetary mission ever sent has worked exactly this way, because traveling along the plane is cheap. Leaving the plane, though, is anything but cheap. In fact, it's one of the most expensive things a spacecraft can possibly do. And the reason comes down to a single concept engineers obsess over: delta V. Delta V is the total change in velocity a spacecraft can produce using its engines. Think of it as the currency of space travel. Every maneuver, every orbit raise, every course correction, every landing burn carries a specific delta V cost. A spacecraft launches with a fixed budget determined by how much fuel it's carrying and how efficiently its engines burn that fuel. Once the delta V runs out, the mission's over. There are no gas stations along the way, every drop of fuel matters, and every maneuver is competing with all the others for that same limited budget. Changing an orbit's tilt, meaning rotating its plane away from the ecliptic, comes with a disproportionate and brutal delta V cost. The physics here is clear but merciless. To change your orbital plane, you have to fire your engines perpendicular to your direction of motion. You're not speeding up or slowing down, you're rotating the direction of your velocity without changing its magnitude. How much delta V you need depends on two things: how fast you're already moving, and how big an angle you're trying to rotate through. And the faster you're going, the more brutally expensive a plane change becomes. That's the merciless core of the whole problem right there. In low Earth orbit, a spacecraft moves at roughly 7.5 kilometers per second. At that speed, a 1 degree change in inclination costs about 140 meters per second of delta V, a manageable cost for small corrections. But even in low orbit, a 90-degree plane change, say turning an equatorial orbit into a polar one, requires roughly 11 kilometers per second of delta V. That's actually more velocity change than it takes to get the spacecraft from the ground into orbit in the first place, which means it would actually be cheaper to come back down and relaunch from a different site than to change planes while already in orbit. Now take that same idea and apply it to a sun-centered orbit. Earth moves around the sun at 30 kilometers per second. At that speed, a 90-degree plane change requires roughly 42 kilometers per second of delta V. For comparison, Getting from the ground to low Earth orbit costs about 9.5 kilometers per second. Fully escaping Earth's gravity and entering a transfer orbit to Mars costs around 12 kilometers per second. Even the most powerful interplanetary missions ever launched have worked with a total delta-V budget of somewhere between 10 and 15 kilometers per second, counting everything from the launch pad onward. 42 kilometers per second isn't within reach of any rocket ever built. It won't be within reach of any rocket being designed in the near future either, because the fuel needed for chemical propulsion grows exponentially with the delta-V you're asking for. Doubling your delta-V doesn't just double your fuel. The fuel-to-payload ratio you need basically squares. The amount of fuel needed for 42 kilometers per second would weigh many times more than the spacecraft itself. You'd need a fuel tank the size of a mountain just to move a vehicle the size of a phone booth. This is exactly why going up in the solar system is, for all practical purposes, impossible through brute force. The planet's sideways speed is just too enormous, and the cost of redirecting that speed is way too extreme. You can't just point your spacecraft perpendicular to the ecliptic and fire the engines until your orbit rotates. The numbers just don't add up. There isn't enough fuel. A rocket like that simply can't be built. And yet, back in 1990, the European Space Agency and NASA launched a spacecraft that pulled off exactly this seemingly impossible feat. It flew over the Sun's poles, on an orbit tilted 80 degrees, almost perpendicular to the plane the planets travel in. The mission was called Ulysses, and how it managed to do this tells you more about the true nature of getting around the solar system than almost anything else could. Ulysses didn't muscle its way out of the ecliptic. No rocket could have done that. Instead, the mission's designers found a gravitational loophole 500 million kilometers from the Sun at Jupiter, which has a stronger gravitational field than any other planet in the solar system. The plan was bold. To reach the Sun's poles, Ulysses would first make a 16-month journey from Earth to Jupiter, covering almost 1 billion kilometers. At Jupiter, the spacecraft would pass close enough for the planet's massive gravity to grab its orbit and violently fling it off the ecliptic. Jupiter would act like a cosmic slingshot, converting the spacecraft's forward speed into a climb way above the plane. The gravity assist maneuver is one of the most elegant tricks in orbital mechanics, and understanding how it works shows exactly why it's so essential for missions trying to break out of the plane. The principle is deceptively simple. A spacecraft approaches a planet on a hyperbolic trajectory, too fast to get captured into orbit, but slow enough to get significantly deflected by gravity. As the spacecraft falls toward the planet, it speeds up. As it swings around and pulls away on the other side, it slows back down by that exact same amount. Relative to the planet, the spacecraft leaves at the same speed it arrived. No energy gained or lost. The whole encounter is perfectly symmetric. But here's the trick. The planet isn't standing still. It's orbiting the Sun at a tremendous speed of its own. The moment you shift your reference frame from the planet to the Sun, that symmetry breaks. The spacecraft's speed relative to the Sun changes dramatically depending on the geometry of the encounter. If the spacecraft passes behind the planet in the same direction as its orbital motion, it gains speed relative to the Sun. The planet's own orbital speed gets added onto the spacecraft's departure speed. The spacecraft leaves faster than it arrived, and that energy comes straight out of the planet's orbital momentum. In exchange, the planet loses a tiny amount of orbital energy. Every single gravity assist slows Jupiter down by an immeasurably small amount. Jupiter's mass is so enormous that this change can't be detected by any instrument. The spacecraft, meanwhile, gains or loses thousands of meters per second. It's a bit like throwing a tennis ball at a moving train. The ball bounces off at a different speed, but the train doesn't even notice. For a mission like Ulysses, the the gravity assist delivered something even more valuable than speed. It changed the direction of that speed. By carefully choosing the approach geometry, the arrival angle to Jupiter, the closest approach distance, the orientation relative to Jupiter's orbital plane, mission designers could control not just how much the orbit would bend, but which direction it would bend in. Ulysses's approach was engineered so precisely that Jupiter's gravity deflected the spacecraft downward, below the ecliptic, sending it onto a long elliptical orbit that dove below the plane of the planets, passed under the Sun's south pole, then climbed back up toward the North Pole. The planet didn't just speed the spacecraft up, it rotated the entire orbital plane, a maneuver no rocket engine could ever pull off. This maneuver was in no way cheap. To reach Jupiter, Ulysses had to spend 16 months travelling almost 1 billion kilometres in what was, in a sense, the wrong direction. The spacecraft needed to study the Sun's poles, and it did it by first flying 5 times farther from the Sun than Earth is. This roundabout route was unavoidable. No other planet has enough gravitational pull to produce the plane change that was needed. Venus and Mars are too small, Saturn is too far away, and poorly positioned. Only Jupiter combined enough mass with an accessible enough distance to serve as the deflection point. The mission's whole architecture was shaped not by what scientists wanted, but by what physics would actually allow. Over the course of Ulysses's roughly 19-year mission, the data it gathered fundamentally changed solar physics. It turned out that the solar wind coming from the Sun's polar regions was remarkably fast, steady, and predictable. Unlike the turbulent, chaotic wind coming from the equatorial region, this discovery showed that the Sun produces 2 fundamentally different kinds of wind, depending on latitude. Solving an engineering problem ended up cracking open a whole new layer of knowledge in solar physics. It was a bonus discovery, one that would never have been possible without the mission's gravitational architecture. Right now, about 100 million kilometers from the Sun, a small spacecraft is waiting to fly past Venus. It's not there to visit the planet. It's there to steal a gravitational nudge from it, to raise its orbit not by centimeters, but by degrees, one small step at a time. This is basically the exact opposite strategy of the bold one-shot maneuver Ulysses pulled off with Jupiter. And that contrast shows just how ruthlessly the cost of changing direction in the solar system depends on the mass of the planet you're borrowing from. This spacecraft is called Solar Orbiter, a mission launched by the European Space Agency in 2020. Solar Orbiter can't take the route Ulysses used. Its instruments were built to observe the Sun up close, and a trip out to Jupiter would take it way farther out than its thermal design could handle. So instead, Solar Orbiter takes a completely different approach, patient and methodical, gradually tilting its orbit not in one shot, but in small steps, using repeated gravity assists from Venus. Here's how the strategy works. Solar Orbiter's orbit was designed to be in resonance with Venus, meaning the spacecraft swings back close to Venus every few orbits. With every close pass, Venus's gravity tilts the orbital plane up by a few more degrees. This process is slow. During a flyby in February 2025, Solar Orbiter passed Venus at a distance even closer than the International Space Station's altitude above Earth, and that pass bumped the spacecraft's tilt from about 8 degrees up to 17 degrees. The next flyby, coming in December 2026, will push it up to around 24 degrees. With more flybys after that, during the mission's extended phase, the tilt could reach as high as 33 degrees. The difference between Ulysses and Solar Orbiter is honestly striking. Ulysses hit an 80-degree tilt in a single encounter with Jupiter. Solar Orbiter, on the other hand, needs almost 10 years of repeated Venus flybys just to reach 33 degrees. That gap comes down entirely to the mass of the planet doing the assisting. Jupiter is over 300 times more massive than Earth. Venus is only about 82% of Earth's mass. Jupiter can bend an orbit by dozens of degrees in a single pass. Venus can only nudge it by a few degrees at a time. Which planet you pick for your gravity assist is basically the single biggest factor deciding a mission's timeline, its trajectory, and how much tilt it can actually reach. Since Ulysses, several concepts dedicated to observing the sun's poles have been proposed, studied, and eventually shelved, every single one defeated by that same fundamental energy problem. One concept studied in the early 2000s proposed using a massive reflective sail, pushed by the pressure of sunlight, to gradually move a spacecraft into a high-inclination orbit. The sail would have been over 100 meters across, carrying a small science payload, but slowly raising the orbit over months and years through the tiny accumulated push of reflected photons. The concept was technically feasible in principle, but the engineering challenges were serious. A solar sail that size would have been one of the largest structures ever deployed in space, and its material would have had to survive years of intense solar radiation, thermal cycling, and micrometeorite impacts. In the end, the development costs and technological risks were judged too high for the available budgets, and the concept never made it past the study phase. Other proposals came up too, similar solar sail ideas with different orbital parameters, or concepts aiming to reach a high inclination through years of continuous low-thrust burns using ion propulsion systems. Every single one of them ran into the exact same wall. The energy needed to change the tilt of a sun-centered orbit is enormous, and every proposed solution either needed propulsion technology that wasn't mature yet, or a mission duration so long that spacecraft reliability itself became the limiting factor. The persistence of these proposals, and their repeated failure to move past the study phase, tells its own story. The scientific motivation is strong. The engineering community knows perfectly well which instruments are needed and which observations would be groundbreaking. The obstacle isn't a lack of imagination or scientific ambition, it's the raw physics of changing an orbital inclination. The Voyager missions show this same principle from a totally different angle. Voyager 1 launched in September 1977, and it's currently moving away from the Sun at a tilt of about 35 degrees above the ecliptic plane. Voyager 2, launched a few weeks earlier, is diving about 48 degrees below the plane. At first glance, these steep departure angles might look like a deliberate attempt to explore above and below the plane of the planets. But they weren't. They were a side effect. Voyager 1's trajectory was designed to fly past Jupiter, then Saturn, and make a specific close encounter with Saturn's largest moon, Titan. The geometry needed for that Titan encounter bent the spacecraft's path sharply northward, away from the ecliptic. That wasn't a decision to go up, it was simply a consequence of the flyby geometry required to observe Titan from the right angle. After Saturn, Voyager 1 had no more planetary targets left to visit. Its trajectory was now locked in, carrying it up and outward forever. Not because anyone wanted it to go up, but because the Saturn encounter sent it there. Voyager 2's story is similar, but in the opposite direction. After visiting Jupiter and Saturn, Voyager 2 continued on to Uranus and then Neptune. The Neptune encounter was designed to include a close pass by Neptune's moon Triton, and the geometry needed for that approach sent the spacecraft sharply south, below the ecliptic. Again, the departure angle was a byproduct of the gravity assist maneuver, not a conscious decision to go explore below the plane. Both Voyagers are now in, or approaching, interstellar space, and their trajectories carry them a little farther from the ecliptic with every passing year. This pattern shows up again and again throughout the history of spaceflight. Whenever missions leave the ecliptic, they do it through gravity assist maneuvers, not engine power. Whenever they reach high inclinations, it's because some massive planet redirected them, not because their engines pushed them sideways. The architecture of every out-of-plane mission ever flown or even planned relies on borrowing momentum from a planet, because generating that momentum independently is simply beyond the reach of any propulsion system that exists today or is likely to exist in the foreseeable future. So what does this whole story tell us? The very first direction we learn as humans is up. Before we could talk, before we could tell left from right, gravity had already taught us that. Every time we got picked up, every time we reached toward a face above us, every time we fell and the ground caught us from below, that lesson got reinforced. Throughout history, every civilization organized itself around this axis. Temples rose upward, graves were dug downward. We say spirits rise, we say moods sink. A promotion is a rise, a failure is a fall. Even our moral universe borrowed its geometry from the physical one, because the physical felt so absolute, so obvious, so permanent. But it was never actually permanent. It was always a local concept. The direction you call up is defined by exactly one fact. You're living on the surface of a massive sphere, and gravity is pulling you toward its center. Away from that center is up, toward it is down. That definition works perfectly everywhere on Earth. But it only works because every person who's ever lived has shared that exact same gravitational reference. The moment you remove that reference, the moment you leave the planet and enter a universe where gravity comes from multiple directions and no single surface defines a floor, the word up doesn't slowly adjust to the new conditions. It shatters. This shattering isn't a metaphor. It's something that genuinely happens in human spatial reasoning. Astronauts describe this consistently. The moment they first reach orbit and the felt pull of gravity disappears, their brains struggle to rebuild any sense of orientation. Some astronauts experience a constant sensation of falling. Some feel like the room has flipped upside down and that they're the ones stuck to the ceiling. This disorientation can last for days. The brain, which has been searching every sensory channel for that gravitational signal present in every waking and sleeping second since birth, finds nothing there, not weakened, not distorted, just completely absent. At this point, isn't the real question we should be asking, if up is this fragile a concept, is what makes it feel so solid really physics? Or is it just a habit of a species that evolved on one particular planet? And this is exactly where every observation across the solar system leads us to the same conclusion. Direction isn't a property of your surroundings. It's a relationship between an observer's motion and the gravitational field they happen to be in. Change the source, and direction changes. Remove the source, and direction disappears entirely. And yet people keep clinging to this word. When people first learn that the solar system is flat, they almost always ask the exact same question. why don't we just go up? Why not just fly a spacecraft above the plane and look down on everything from up there? That question feels natural because it's carrying an intuition built for Earth into a space that has no foundation for it at all. On Earth you can go up, you jump, you climb, you fly, and gravity resists but allows it. The energy cost is real but manageable. In the solar system, though, the direction perpendicular to the ecliptic exists geometrically, but it has no special physical status. It's not an escape from the plane, not a shortcut, not some neglected or overlooked dimension. It's just a direction, one out of an infinite number of directions. And reaching it from within the ecliptic means overcoming that enormous sideways speed carried by every object in the system. Rockets do launch upward from Earth. That's true. But once they reach orbit, the word up means nothing more than a simple question, one that carries a price tag almost no mission can afford. The solar system's flatness isn't a wall. It's a tax, paid in delta V, spent in fuel, and imposed by the inherited speed of a 4.5 billion-year-old disk, a tax that no human technology has ever managed to get around. Gravity taught you this before you were even born. It reinforced the lesson every time you were picked up, every time you fell and the ground caught you. But beyond your planet, nothing offers you that same gift. There's no universal reference frame, no free direction. Direction has to be chosen, orientation has to be defined, every path has to be paid for. And the currency for that is speed, and the price is steep. The solar system doesn't have a top, it doesn't have a bottom. What it has is a plane, defined by history and angular momentum. And everything inside it moves along that plane, because it all came from the same spinning disk. The direction perpendicular to that plane is real, reachable, and physically valid. But it isn't up. It isn't some natural destination. It isn't a direction the universe is inviting you toward. It's a direction that has to be carved out of the momentum you're already carrying, paid for in the deepest currency physics has. Every kid who points at the sky and says up is saying a word that will mislead them the moment they leave Earth. Not because the universe is cruel, but because it's indifferent. It doesn't hand out directions, it doesn't label its axes, it doesn't tell you which way to go. It just gives you speed, gravity, and the conservation laws, and leaves the rest for you to work out on your own. And maybe that's exactly where our real greatness lies, in being able to chart our own direction, all on our own, without needing any universal compass, without needing any up. So what about those distances between the planets? Are they really as innocent as they seem? Or are they hiding something far bigger? In the next episode, we're going to find out together that the real distance between planets is actually way more unnerving than you think. Don't forget to subscribe to the channel and like this video so you don't miss out on getting to see it first. Our journey tonight ends here. I'll leave you with one thought in the silence of the stars. Maybe the real skill was never about finding a direction. Maybe it's about creating your own. Good night, sweet dreams, and I'll see you again tomorrow under that same sky.